Welcome to session 1 on tools and technologies of the 13th module on big data management and machine learning. In the previous module, we have learned about big data management, various use cases that pertains to big data management in smart grid, and we have seen some of the examples of big data management and how it can help grid analytics. In this module, we will focus on tools and technologies that can enable processing of big data. In this session, we will talk about many open source tools and technologies which are being used in the industry, and we will also talk about how R programming can be used to analyze smart meter data. So in this session, let's get on with understanding various open source tools and technologies. There are many tools and technologies that are available. I have listed down 9 of them. Starting with Hadoop, we'll spend more time on this technology because we have seen large scale adoption of Hadoop in the industry. Apache Spark, which is overcoming some of the drawbacks of Hadoop and providing a general purpose computing platform. We'll also spend a little bit time on that. Then rest of the tools like Apache Storm, Cassandra, MongoDB, R programming tools, Neo4j, Apache, Samo, HPCC, we'll briefly touch upon. Let's look at each one of these and just try to understand at very high level. The very first one is Hadoop, the long-standing champion in the field of big data management and known for its capability to process huge amount of data. You could deploy Hadoop on premises or you could use Hadoop from cloud. There are many cloud service providers, including IBM, that provides Hadoop services on their cloud. The advantage of using Hadoop from cloud is that you get auto scaling, you get infinite scaling as well. The second tool, Apache Spark, which was built to address the shortcoming of Hadoop. This is a very powerful tool. It allows the general purpose computing as well as processing big data, working with graphs, as well as you can run machine learning libraries in the Spark. Apache Storm, a real-time framework for data stream processing, which supports many programming languages. Storm Scheduler balances the workload between multiple nodes based on topology configuration and works well with Hadoop HDFS. Next 3 tools are Cassandra. This is again from Apache. This is a database, is the right choice when you need a scalability and high availability without compromising performance. Linear scalability and proven fault tolerance on commodity hardware or cloud infrastructure make it the perfect choice. Next tool is MongoDB, built upon the speed, flexibility, and power of document module. So this is a NoSQL database where you manage your information as set of documents. The capability of its distributed system design and the freedom to run anywhere. MongoDB enables you to standardize your app on a single modern data platform. R programming is a language which is used to process big data when it is deployed on Spark. But this is the language which is of choice for many data scientists for performing analysis of time series data, other big data, to quickly understand the value you get from the data. This is a very powerful tool. We will show a hands-on example of R programming in the subsequent session. Other three technologies are Apache Somo. This is one of the another Apache Foundation tool. Specializes at building distributed streaming algorithm for successful big data mining. This tool is built with pluggable architecture and must be used upon. This tool is built with pluggable architecture and must be used along with other Apache products. Neo4j is an open source graph database with interconnected node relationship of data, which follows the key value pattern in storing data. The last one is HPCC, also known as DAS, Data Analytics Supercomputer, data intensive computing system platform. The HPCC platform incorporates a software architecture implemented on commodity computing cluster to provide high performance and data parallel processing for application utilizing big data. So these open source tools and technology can help you process big data, meaning it can work with huge volume of data. It can also work with streaming data that takes care of the velocity aspect of big data management. And many of these tools are used to process not only your structured data, but also unstructured data like your document, like your design artifacts, like your video streaming data. And of course, with this tool, we can maintain the veracity of data by securing it by using algorithm to estimate missing data. So let's spend some time understanding the details of Hadoop, because this is one of the early systems which provided the industry-wide adoption. So Hadoop, the way Hadoop works is different than the regular programming model. I'm sure you must have done some programming. Say you are building an application with Java and you are writing a Java application. In that application, you may be, say, processing a student's record, and when you to find out what is the number of marks a student have got from multiple subjects, what you do is using JDBC, you get the data, bring it to your application, process the data, get the result, and then you can store the result back to your database. But when you talk about Hadoop, which also uses Java, but the pattern used in Hadoop is here we don't bring all the data to the application. Instead, we let the data spread across multiple nodes and let your program process this data where it resides. This way, we can address the challenge of big data, because it is not possible to bring all the data to application and process it. So this new paradigm in Hadoop has resulted in many capabilities to build big data system. One of which is the scalability, and this is largely because of the Hadoop file system, which is called HDFS, Hadoop Distributed File System, which can run on commodity hardware, provides fault tolerance as well. And that is the reason, you can scale Hadoop infrastructure to the scale you want. some of the world's largest Hadoop implementations runs into thousands of commodity hardware, and we use their services day in, day out. When we do search on any of the search providers interface, data goes back to Hadoop system where it processes it and provides the result back. It is cost-effective solution because the whole system is running on commodity hardware. It is flexible because you can process variety of data, including images, video data, as well as structured data. It is fast. Hadoop uses a storage which is infinitely scalable and uses a programming model called MapReduce. Combination of these two provides fast processing of the data because you can perform parallel operations across number of nodes. Security and authentication. As we have seen in smart grid, security is very, very important. And big data management system ensures that the data acquired and kept in big data management system is not compromised. That is why it allows you to maintain the encrypted data in your system. And of course, parallel processing helps you process the data faster. Other dimensions are availability and resiliency of the system. The Hadoop system is built with a thought that systems are made to fail. That is why data is maintained in multiple places. Even if one of the system fails, the overall system is still intact and able to process information what it needs to do. It uses a very simple programming model called MapReduce. We will spend some time on understanding how MapReduce works. When we look at Hadoop, there are two parts of this architecture. The first one is Hadoop file system, which is called HDFS, and another one is the MapReduce for processing data. We have already seen how Hadoop file system helps in managing data, and the MapReduce with the operation of performing map function and then applying the reducer to get the result. Let's look at Hadoop distributed file system architecture. So HDFS has three key components. The first one is data block, second is name node, and the third one is data node. Here you see in data block there is a default fixed length size of data block which is 64 MB, but you have the flexibility to define your own data block which can be of any size, but the fixed size provides some advantage. The fault tolerant through replication within the node as well as across the node provides the exceptional resiliency aspect of HDFS. If you look at the example, so here you see there are yellow boxes within which there are green boxes. So suppose the green box is a data block, then system maintains 2 copies of any data block in one node and it replicates this data block to another node so that if one of the hardware fails or one of the node fails, assuming each of these nodes are running on different rack, your system is still highly available. Metadata can also be stored separately. Now let's look at name node. So name node manages the file system namespace and regulates client's access to files. It maintains the file system tree and metadata for all files and directories in the tree. In the version 1 of Hadoop, there used to be only one name node, and most of the time that used to be the single point of failure. To mitigate the problem of single point of failure, in version 2, name node was introduced in active passive mode such that if any one of the node fails, the other node takes over and provides high availability to the whole cluster. Next one is the data node. Data node is where we stores and retrieves the data in blocks and periodically reports to name node the list of blocks which is being stored in data node. Client can directly access the data node, and most of the work, the actual processing of application happens on the data node. So we have seen the first aspect, which is HDFS and its architecture. Now let's look at MapReduce. So MapReduce programming paradigm, there are 4 phases in MapReduce, even though 2 of them are more prominent, but other 2 kind of plays a supporting role. The very first phase is the map phase. Then comes the shuffle phase, followed by reduce phase. And the last one is combiner phase, which is also known as semi-reducer phase. So in this diagram, you see how data is first converted into tuples using maps, and then these tuples, which has the key value pairs, are sorted out, and then the reducer function is applied to reduce the output, which can again be processed with next chain of MapReduce function. So to get the final result, you can build chain of MapReduce algorithm to arrive at the final result. So let's look at map phase. So map phase is a small program distributed across the cluster, which is local to data. It hands a portion of input data. Each mapper parses, filters, or transforms its input, produces group data, which is in key value pair. Shuffle phase, output of each mapper is logically grouped together by key. One of the node is chosen to process data for each unique key, and all of this movement of data is transparently orchestrated by MapReduce. The next phase, which is the reducer phase, it takes the shuffled data and applies the reduce algorithm to generate the reduced output. Then you have the combiner phase, which is the optional phase, and it acts as a semi-reducer. So let's find out word count using MapReduce algorithm. Here we have large amount of data. These are distributed across multiple files, and each of these files has names of different fruits. So what we need to do is count how many times each of these fruits are appearing in total. So we apply the MapReduce algorithm to first create the tuples where we have the key and value. And here key is your name of the fruit and the value is how many times it is appearing. In the subsequent slide, we'll see how that works. So here you have the list on the left, which is the input provided to you. Then mapping function is called. So what it does, it rearranges the data and creates these tuples. So you see in the first block, we have apple as 1 unit, right? And then the other fruits are mentioned with how many times it is appearing on the list. This way, map function creates a set of tuples. Then it shuffles and brings all the apples into first box. Thereafter, the reduce function is applied to calculate the count of values for a specific key. And thereafter, you get the result in terms of how many of each fruit is present in that particular list. This programming model is little different than applying a regular algorithm. But the beauty of this model is you can push this MapReduce logic to your data node and perform the tasks in parallel on thousands of nodes, which is what is needed to process the big data. There were some deficiencies in Hadoop. It was mostly suited for processing batch data. Because if you have to process streaming data, then probably Hadoop is not the right choice. That is why we have Spark, which is once again part of Apache Foundation project. So Apache Spark is a distributed in-memory computational framework which allows for fast interactive cluster computing. One of the beauty of Spark is its easy to use APIs for operating on large set of data. It is much faster than Hadoop, almost 100 times faster. And this attributes to the in-memory processing of data. It is also a general purpose computing. So you can perform many capabilities in Spark. You can process big data that includes streaming data, different varieties of data, as well as you can apply machine learning algorithms in Spark. It has set of pre-built libraries which can be called from the program, and you get the results out of those machine learning models. It is infinitely scalable as well. You could deploy it on-premise or you could deploy it on the cloud. Once again, there are many cloud providers, including IBM, provides Spark on the cloud. Needless to say, Spark is also fault tolerant. Let's look at the Spark architecture, what it provides. So in the center, you see a big bar, which is Spark core. And then on the top left, you have Spark SQL. We developers are now very familiar with querying structured data by writing SQL, structured query language. So Spark provides Spark SQL, using which you can query data very easily. It has Spark streaming component, which allows you to process streaming data coming into your platform. Many of the smart grid data, specifically data coming out from PMUs, even from many of the sensors deployed on various assets, may require stream processing. So Spark provides streaming data as well. It has mlib libraries, which is machine learning libraries. You can run number of machine learning algorithms. For example, you want to learn random forest algorithm. You could call the random forest algorithm in Spark, use the data which you are analyzing, create the model, train the model, and then use that model to get additional insights. In subsequent sessions, you learn more about machine learning. And Spark currently in the industry is a preferred means of performing many of these tasks. Spark also allow you to process graph data. As we are seeing, relationship among different entities and the data generated from these entities has to be combined in such a way that we are able to maintain the relationship aspect. Its cluster manager could be Yarn, Mesos, or the standalone scheduler. Spark, as I mentioned, could be used from cloud or it could be deployed on premise. Now, let's look at one of the deployment of Spark on Hadoop infrastructure, and this tool is called IBM Analytics Engine, which combines the power of Spark and Hadoop services. It is a modern and cloud infrastructure. This is also available on-premise implementations. You can create clusters of IBM Analytics Engine in a minute. It is open and ODPI compliant. It provides administrative interface. It provides both the Spark and MapReduce capability, and it integrates with Watson Studio and many other tools. One of the key features of IBM Analytics Engine is it is decoupling the processing capability, compute, and the storage. In regular Hadoop implementations, your HDFS and the compute is together, whereas in the IBM Analytics Engine, you can decouple the storage and you could use external storage like object storage, and you can have compute. So you can have your data reside in object storage, but you apply or create the compute node in Analytics Engine and process this data. You can apply machine learning models in this environment, get the results and store it back in object storage, or any other storage of your choice. So in this session, we looked at many technologies. Many of them have come from Apache. We looked at Apache Hadoop in more detail. Then we briefly touched upon Spark, followed by IBM Analytics Engine. In the subsequent session, we will talk about how we can use R programming language to process smart meter data. In that session, we will use one example smart meter data and then apply R programming to perform various visualizations. Thank you.